let's get going with some discrete math. Any requests? Okay, I'll make it up then. So, we've been talking about proving things, which is awesome. We've proved a bunch of, mainly like we proved a bunch of things about the rational numbers, the irrational numbers, the integers, all that. We're proving things about infinite sets now for the first time, which is exciting. We should not lose how interesting that is, that math allows us to do things with infinity that really nothing else, no other topic really does. But yeah, so today let's finish off what I wanted to do last time. And that is, oh, I should plug this in, that'll help. And that is do one last one of these closure proofs. Move on to more interesting things. Not that closure's not interesting. I wish I had some closure in my life. I still don't have closure for elementary school. I always felt like I was gonna go back, but I never did. Okay, anyway. So, let's look at the following claim. The claim is the irrational numbers are closed under division. Okay, so the first thing we do is we always write it formally, right? We take a claim, we write it in formal mathematics because theoretically this could be interpreted many different ways maybe, but formal mathematics is like this can only go one way. This is what this means. Everything is very, very rigorously defined. So let's get rigorous. What is the definition of saying something's closed under division? First of all, is it an existential statement or a for all statement?
For all.
Exactly, right? Because you're saying for all x and the irrational numbers, which if you can remember, we write as the real numbers. We do this like /q, because the / when we get to set theory, what that's going to mean, it's going to mean take the real numbers and take out all the rational numbers. That means like take out. So this is the real numbers taking all the rational numbers, which is exactly what the irrationals are. But for all x and the real numbers, take out the q, so all x and the rational numbers. And for all y,
Professor, a quick question.
yeah.
Why don't we use like small letter I to say irrational? Because that's what we write in math, like doing like general math.
Oh, really? You could.
That's imaginary because that value doesn't exist. So we use a small I.
A small I like this?
Yeah.
Oh, well,
There's a difference
mean
between the irrationals and imaginary complex.
Oh, okay. So yeah. Thank you, Alex. So these right here are imaginary numbers, and these are a different thing. The irrational numbers. So the real numbers, these are all fractions, or otherwise known as things with decimals that end or repeat. So for example, this is like 0.3s in here. Or 0.56565656 is in here, or 1 is in here, or 2.375 is in here, right? That's what a rational number is. Now, a real number, which I think is what you're thinking about, like I think you're kind of getting rational and real mixed up. A real number is just anything on the number line. So just literally any point you can pick on the number line, including things like pi, the square root of 2, and -e, all those things are real numbers. So there's no imaginary numbers here. The real numbers are just all the numbers on the number line. So we're not getting any complex numbers or anything like that. The rational numbers are specifically numbers on the number line that have decimals that are nice, that either end or repeat. The irrational numbers, so the real numbers minus the rational numbers, take out the rational numbers, these are things like pi, which equals 3.14159265 something, right? Or e, which equals like 2.7, and the decimals go on forever and they don't repeat. Or the square root of 2 is the same way. So that is what a irrational number is. They're not imaginary numbers. They're just real numbers, so numbers on the regular number line that have decimals that never repeat and never end. Make sense?
Yep.
Yeah. So they're even easier in a certain sense. Yeah. Yeah. We're not going to touch imaginary numbers in this class, except for maybe me giving like a fun fact here or there and going, isn't that cool? And then I wait for a while, then like Tori will give a thumbs up in the comments, and I'll be like, nice. But anyway, yeah. So this means just any irrational numbers are closed in a division. This is a for all statement. This is a for all statement that says that for all x in the irrational numbers and for all y in the irrational numbers, x over y is in the irrational numbers. The point is it's a double universal statement because it has to work for all x and y. All right, let's first do an aside. So do we think this is true or false? I think one thing that might give this hope is when we said the rational numbers weren't closed on a division, right? What was our big issue? Like what was the problem child there?
Division by 0, right?
Division by 0. So I'll say note though, is 0 a rational number? Or irrational is what I meant to say. 0 a rational number?
Wait, is 0 a rational number? Yes.
Or it's like irrational.
Okay,
Is 0 an irrational number? Yeah.
No.
No, exactly right. 0 is not in a set of irrational numbers. So that might give us a little hope. But so here's the question though. For any general irrational numbers, is x over y going to be in? What do you guys think?
No, because you could have 2 of the same irrational number, and that would get you 1, right?
That's an excellent point. That's an excellent point, right? So you might think this makes a little bit of sense because, I don't know, if x can't be written as a fraction and y can be written as a fraction, then you'd kind of think certainly x over y can't be written as a fraction because if it could be, you'd think maybe like one of them would be irrational or something. But, I mean, think about this. What if you just did pi over pi? Or pick any one of your favorite irrational numbers, that just equals 1, which is very rational. So the point is, this is our counterexample. This is an example of an x and a y that are in the irrational numbers, but the division is not. So they're not closed. You can get out of the irrational numbers by dividing two irrational numbers. Make sense? Yeah, yeah. The irrationals are in an open relationship with division. So, there's gonna write the proof. And so the proof is gonna be a formal way of kind of writing what I just said. Oh, we got a chat. All right, so the proof, right? This is a counterexample proof. So this isn't, we don't have to use like direct proof or anything like that. We're not proving anything. We don't actually have to prove something about an infinite set here because we show it doesn't work. So we just define one counterexample that's a universal statement. So really this is a disproof, I should say. And so what we're gonna do here is we're gonna say disproof by counterexample. Let x equal pi and y equal pi. Note, pi is famously irrational. So x is an irrational number and y is an irrational number. All I'm saying here is that it's known that pi is an irrational number. That's another thing you can assume for this class, I guess, although theoretically someone had to prove this at some point. But it's a little bit above the scope of intro to discrete mathematics. It's also transcendental, which is another fascinating thing. Transcendental, this is a total side note here. An algebraic number is a number that is the root of some equation. So here's what I mean by that. The square root of 2 is irrational. The square root of 2 equals like 1.6, what is it? 1.8 or something like that. But it goes on forever. They just never repeat. It goes on forever, right? So the square root is irrational, but the square root of 2 is a root to this equation, right? That's what it means to be an algebraic number. Algebraic numbers are numbers that are roots to equations like this, right? And so you can have even more complicated things. Like what if you have like x cubed minus 4, x squared plus 3x plus 5, something like that, right? All the roots to this would be an irrational number. And they could be weird. They could be things like the cube root of the square root of 2 plus 5. It could be weird things, right? Those are all algebraic numbers. Transcendental numbers are numbers that cannot be written as a root of any equation or of any polynomial like this where you have rational coefficients. And the pi is one of those. No matter what polynomial you come up with rational coefficients, you won't get pi as a root. Pi is super weird, and it's a whole thing. That's all math history. That took forever to prove. But anyway, that's not important. The point is pi is famously irrational, so x is in rational numbers and y is in the irrational numbers. So remember, this is important right here. Right here, what we're doing is verifying that our counter example is in our domain. And we always have to do that for a counterexample. Because it wouldn't be enough to come up with two numbers, right? That you divide them aren't irrational unless they actually are in the irrational numbers. We're saying things about the things in the irrational numbers. So we couldn't have like x equal 1 and y equal pi because 1 would be irrational. The point where it's verifying this is saying, we're verifying we're actually talking about the things we're talking about. So x and y are both irrational. Then x over y equals pi over pi, which equals 1, which is in Q. Therefore, x over y is not in R over Q. And that basically proves it. Thus, there is some x in R over Q and some y in R over Q mainly x equals pi and y equals pi such that x over y is not in R over Q. Therefore, there we go. Therefore, R over Q is not closed under division. Squarey thing. QED, we're done. Any questions? I think this is pretty straightforward, right? Yeah, we just in the one case it fails pi. We just and then really formally what you do is you say disprove my counterexample. You need to say that. You point out what the counterexample is. You verify the counterexample is actually in the domain you care about, and then you show that it fails the condition. And that's your proof. The point is to write formal proofs, right? They need to look something like this. So your homework 6 is going to be basically all proofs, and they all need to have this nice formal form. You say every little detail and all that kind of stuff. Cool. Well, so